Free body diagrams. Let's take a few minutes to really get these down. You want to be able to do nice free body diagrams. You want to be able to do them quickly, and so you want to have them down because you're going to be using them all quarter long. You're going to be using them all next quarter when you're dealing with electric forces and magnetic forces. Physics builds on itself. If you don't have a good foundation now, it's going to hurt you later down the road, next quarter even. So let's try to get a good foundation here for free body diagrams. It really helps you set up the problem nicely and gives you a good start on solving the problem correctly. A lot of students like to skip the step of drawing a free body diagram because it takes a few seconds, right? It takes a little bit of time to do it, and they don't think they have that time. But if you want to get the problem correct, it's worth taking those few seconds. It's a great tool for setting up Newton's Law problems. So we're going to go through a few scenarios here just to give you a grasp. We'll start out with some that are fairly simple, and we'll work up. We'll add friction, then we'll add an incline and get a little more complicated. But right now we're starting with two masses on a frictionless surface. There's a rope connecting them, and you're reaching in and grabbing onto one of the masses, M2, and giving it a tug. So we're going to draw free body diagrams. I'll just put M1. This free body diagram will be here. And right now, all of our objects are just point objects. They have no dimension to them. Because if they had dimension, then they could actually rotate, and then we'd have to deal with more complicated situations that we don't have the tools to deal with yet. You will by the end of the quarter. Well, our objects won't be point objects. They'll be real three-dimensional objects, and they'll be able to rotate, and we'll have to deal with that. But right now, everything's a point object. So when I draw my free body diagram, I just draw a point for my object. There's M1. And my free body diagram has all the forces acting on M1. So the first thing I look at is what is touching M1, because we know that when things touch, there's often a force involved. So I'm looking at M1. What's touching M1? The rope is touching M1. So I'm going to draw a force there from the rope, and the rope is giving M1 a tug to the right, so I'll put my force pointing in that direction. And we usually, with ropes, we call it tension, so I'll use a capital T. And I'm going to be real careful with subscripts here for the first few lessons on free body diagrams. And then as we get more familiar with them, I tend to loosen up a little bit. But I'm going to put subscripts here. The first subscript is the force that this is acting on. So this is a force on M1. So every force in this free body diagram is going to have a 1 for its first subscript. And the second letter indicates what's causing the force, and the rope is causing the force. So this is a tension force on mass 1 due to the rope. I guess I could put a vector hat on it too. It's a vector. Now I look to see what else is touching M1. Well, the ground is touching M1. And the ground can interact in two ways. It can interact parallel to the ground through a friction force, but in this case there is no friction, so I won't include that. And it can interact perpendicular to the ground, or normal to the ground, through a normal force. So I'll draw that one in here. The ground is going to be pushing up with a normal force because it's normal to the ground, or perpendicular to the ground, so we call it N. And it's on M1, and it's due to the ground. And those are the only two objects that are touching M1, the rope and the ground. And we only know of one force right now that can reach in from a distance and influence M1, and that's gravity. So I'll put the force of gravity here. That points to the center of the Earth. And we usually use W because that's what the weight of an object is its force of gravity between it and the Earth. So that's the weight of M1 due to the Earth. Next quarter, you'll learn about electric forces and magnetic forces. They also can interact at a distance. But right now, the only one we know of is gravity that interacts at a distance. So there's M1. I think I've got a complete free body diagram for M1. I'm going to come over here. I'm going to leave some space because I think I'm going to draw the rope also. And I'm going to come over here and draw my free body diagram for M2. Here's my dot that represents M2. And the first thing I look at is to see what is actually touching M2. There's a rope touching M2. That's the tension force acting on block 2 from the rope. There's your hand. We're just calling that F, acting on block 2 from the person or the hand, however you want to indicate that. The ground is touching M2. That ground can interact in two ways, through a friction force, but we don't have that here, and through a normal force. So I'll draw my normal force in on 2 from the ground. And gravity can reach in from a distance. That's the weight of mass 2 due to the Earth. So that's it. I've got the 3 forces due to objects that are reaching in and actually touching M2, and I've got the 1 force, the weight, that's due to an object that's not touching M2. That's due to a force at a distance. And I think I can go back here and do the rope. If the rope is massless, then normally we wouldn't actually draw the free body diagram for the rope because it's not impacting our system. But if the rope has some mass, then we would actually include it as a third object here and draw the free body diagram for it. So there's a dot that represents our rope. It's interacting through a tension force. This is a force on the rope due to mass 1. The rope is getting pulled to the left by M1. And the rope is getting pulled to the right by M2. That's a tension force on the rope due to mass 2. And since the rope is not touching the ground and it's massless, then those are the only 2 forces acting on the rope. Now we can think about Newton's pairs, because what happens next is we're going to write down some equations and try to solve those equations and figure out what's happening, maybe solve for the acceleration or solve for the tension in the rope, something like that. And if you have too many unknowns, you won't be able to solve that equation. So you have to figure out some of these forces are going to be the same. And we're going to use Newton's law to figure that out. And Newton's law tells us that when 2 objects interact, they interact with equal and opposite forces. So we can see that M1 and the rope are interacting. We have a tension on 1 from the rope, and we have a tension on the rope from 1 in the opposite direction. And we know because that's a Newton's pair, because those 2 objects are interacting with each other, that those have to have the same magnitude. So I'm going to put a little line here and a little line here. So I know that those 2 are a Newton's pair and have the same magnitude. I also see there's a tension that interacts the rope with M2 and M2 with the rope. So we've got those 2 tension forces, and I'm going to put 2 little lines there because those are also a Newton's third law pair, and they're going to have the same magnitude. And then I have to look at the tension on the rope due to mass 1 and the tension on the rope due to mass 2 and see how they relate. And because the rope is massless in this case, those will be the same. And then we have then we can say that all of these tensions are the same, and we can just use T to indicate the tension everywhere. But if you have different tensions, then you want to make sure that you indicate it differently with a T1 and a T2, some notation that tells you that the tensions are different in different areas. But as long as the rope is massless, it's going to have the same tension everywhere.